Lusztig City. Welcome to the last day of the conference. First speaker is also Sobaje from University of Georgia Southern University. So there is a combination of communication those works. And out of this is a combinatorics for spatial tilting modules.
Well, thank you, Zhangju. Just want to first start by thanking our organizers for putting together such a wonderful conference. In a sense, it's a shame that it has to come to an end, although I'm out of mental space for mathematics. I am out of clean laundry, so it does have to come to an end. I want to thank Zhangju also because I did not realize my life was incomplete without hearing a rock ballad about Dan Nakano's research. And if you were not at dinner last night, you're going to want to find that song. Well, it's an honor to be speaking at your conference, Dan. I want to say happy birthday. I know we're going to Zoom several times probably before your actual birthday, but this will be the in-person. I feel like everybody has already said the things I want to say, which just speaks to the consistency of who Dan is. He's been the same mentor for so many people in this room. I can say the exact same things that Chris said, that the other Chris said last night, that John said. Well, I didn't meet my partner through Dan, but I can say most of the things that some people said. But as Bill said at the beginning of the week, Dan, you genuinely care for the people you're mentoring, and it's obvious. And he takes real pride in his students and his former postdocs. And so I've gained so much from you mathematically, professionally. You know, Dan's even like he sat down with me and showed me how he filters his email inbox in great detail, which maybe doesn't sound exciting, but Dan has a way of doing things where he frees that time to do mathematics, not by putting off little tasks, but as he would say, by flicking them away and getting them done quickly. And then he thinks about math. And so he's taught me that. Personally, Ruth Elizabeth and Dan have been great to my family. And in fact, they're sitting in the back row here. They wanted to be here for Dr. Dan's conference. So I want to say a few things about Dan's mathematics as I lead into this talk, which is about tilting modules. And so before I ever started working with Dan, his papers were already having a big impact on the way I thought about mathematics and the problems I did. And so a few of those papers that really stand out. The first one was Nakano partial vela, which Dave Benson referenced yesterday. And that paper had a number of results that I needed to compute support varieties, had a number of tools and techniques that sort of led me in the way I thought about things. A second paper was Carlson, Lynn, Nakano. And that one, it wasn't even necessarily the main part of their paper, but it really shifted the way I thought about isomorphisms from nilpotent to unipotent varieties. And so that was another important paper. The third one, which leads really for me, was the starting point of anything that I thought about with tilting modules, was this paper from 2015, Kildatov Nakano. And it was on something called good PR filtrations. It had to do with a number of conjectures that Steve Donkin made at this 1990 MSRI meeting that's been brought up several times. Jay Dude talked about it. There have been pictures. And this really shifted, well, first my interest. I've never stopped thinking about stuff that's come from this paper since I read it. And kind of one of the takeaways is these PR filtrations, which I won't necessarily define right now, but there's something that in a sense are unique to modular representations of reductive groups. I mean, you can make sense of whatever a P filtration is for, say, a quantum group and a P3 of unity. The problem is that if you ask questions about that, there's nothing interesting. It's just sort of trivially true that these filtrations exist. And so what I started to see from their paper and then joint work with Dan, Chris, and Cornelius is there's some real subtleties when you're looking at modular representations of reductive groups, and they kind of need a unique perspective. There's something to be said there that sort of complements a lot of the tools we're getting from other places. So Pramod talked yesterday about geometric representation theory and some of the really big results that is brought to this area. But I think there's also a place for these kind of different questions that I don't think many people have been thinking about. And so I guess if I could sell you on something, it's that these P filtrations are very important, and maybe Cornelius will talk more about those later, at least something related to them. what I'm trying to do is, I got involved a little bit with character formulas, and I've been trying to find something that's more analogous to Weyl's character formula and characteristic P. Now, I threw a very non-mathematical word in here, reasonable, and depending on what you define reasonable to be, you've solved it or you haven't. So I recognize that it's not really saying anything there. But what we'll see is that character formulas have sort of migrated away from something that looks more like Weyl's original formulation. And I've been trying to think about it sort of using the insight gained from the work with Chris, Dan, and Cornelius, and then this paper here. All right, so here's going to be the outline for the talk. I want to start by looking at Weyl's character formula, and then I want to talk sort of about how the history of how things went from Weyl's formula to the way character formulas are done today. And then I want to talk about something that I've been kicking around in a few papers, which is these things I call Steinberg quotients, which are some kind of a character you can associate to certain tilting modules. And yeah, it'd be great if I could convince somebody to think about this with me, because I've been thinking about this a little bit on my own. So let's jump into the setup. So everything I say would apply to a connected reductive group, but let's just say simple algebraic group. For now, algebraically closed field, any characteristic. So you can have SLN in mind. And then T is going to be a maximal torus for G. And I'm sure most people know this, but let me just say, so the aim of characters is you're studying G modules, which can be hard, by restricting them to T. And we do that because the category of T modules is very easy to understand, very easy to write down. It looks the same in every characteristic, the same simple modules, and it's always semi-simple. And so when you do this kind of restriction, you know, you restrict to something easier, you may lose a lot of information and not be able to say much. But some of the things that we do know is in characteristic 0, restricting to T actually can distinguish between non-isomorphic G modules. So if I have modules for my group G and they are finite dimensional, then they're isomorphic over G if and only if they have the same character. And then the simple modules, which everything is semi-simple, their characters are given by Weyl's formula. Well, what I'm interested in is characteristic P. And in characteristic P, the first thing that everybody knows is that the module category is not semi-simple. So when you understand the character of a module, that's only a small part of what's going to go into understanding all the modules in the category. But having said that, finding a character formula for the simple G modules has been basically from the beginning a problem of great interest. And there's been a ton of research over the decades that has gone into this problem and has generated some of the most beautiful and interesting mathematics. And so that's kind of the starting point for this work. So you can say that this has been solved, again, depending on what you define reasonable to be, or we might say this problem has not been solved. I'll explain that. Okay, so I want to just kind of stare at Weyl's formula first, because this is the starting point of everything for us. So some notation downstairs, but I mean, what is this character? Well, it's going to tell us the weight multiplicities of the simple modules in characteristic 0. And the way it's typically presented is like this. And so what do we like about Weyl's formula? Well, the first thing is it's concise. You can write it down very quickly. In principle, you're staring completely at the character of a module, but not all of the information is necessarily readily or obviously available when you stare at this formula, but it is very concise. And one of the most powerful things about it is it leads to the Weyl dimension formula. So playing with this character formula, you can derive a very computable expression for the dimension of the simple module of highest weight lambda. We also, through other techniques, know which weights appear in the Weyl character. So even if we don't necessarily know the multiplicity, we do know which dominant weights appear in this, and we can say certain things about characteristics of how those multiplicities work. Now, it should be noted, because again, I've been thinking about when is a character computable and when is it when is computable maybe not a fair word to say. So if you're staring at the Weyl character of a module, it's not necessarily immediate. Well, it's definitely not immediate. What's the multiplicity of the weight 0, for example, in the module? So you can get there, but it takes some kind of a recursive algorithm or something to compute that. So to be fair, even this character formula, you don't just pluck out all the information by staring at it, but there are various algorithms out there. So this is the beauty of the Weyl formula just as an expression. I did want to pull up a few pictures of Weyl characters for what it's worth. These were generously shared by Joel Gibson, who has this cool program called LeeViz, which enables you to visualize things in Lie theory. And he said, yeah, go ahead and share these. They're kind of simple. I didn't use the full power of what his programs do, but just to look at a few characters. So I took the Steinberg weight 4, 4. If we're working in the prime, p equals 5, then 4, 4 would be the Steinberg weight for SL3. And so what you're looking at here, the set of dominant weights is this shaded region over here. And then what we have here is at each point of intersection where you have a number, that's the multiplicity that weight appears. So the highest weight here is this weight 4, 4. And then in red is the Weyl orbit of that weight. So those all appear in the character. And then we know that everything else that appears is going to be dominant weights that are less than the highest weight in the root ordering. And there's sort of this beautiful picture as to how the weight multiplicities increase. So we can prove from a number of perspectives that the weight multiplicities are going to be monotonic as you go from the outside in. They will not decrease in multiplicity. And here they increase sort of just each level. You also see that the weights appear inside the convex hull of the Weyl orbit. Here's sort of the same weight in type B2. Again, sort of a similar picture, just there's more chambers, more reflecting hyperplanes. But again, you sort of see the same dynamic happening. And then I went to G2. G2 is crazy. And so this thing was way too big to even fit. Well, it was going to be a trade-off of, do I fit the whole picture with numbers you can't read? So anyway, this is the same weight in type G2. But again, you see sort of these beautiful patterns to the way the Weyl characters look. So again, as I was working on these things, I started thinking, when can you compute anything? I'll say more about why I thought about that. And so I'm just kind of going back to basics. I know this is sort of basic stuff, but I don't know, for some of you, maybe it's not. So these are Weyl characters. Okay, so how did we go from the Weyl character formula to the way we currently think of character formulas? And a lot of this, I will say, I borrowed from Janssen has an article on something called character formulae from Hermann Weyl to the present. So this is largely taken from that. But the first comment is that Weyl's formula, which applies to algebraic representations, was initially formulated for and proved with analytic methods. So whenever you have an algebraic statement, you would like to have algebraic proofs for that. So that's the starting point. And there were a number of different people. Freudenthal had the first algebraic proof in the Lie algebra setting. Springer had an algebraic group version. And we have others, Bernstein, Gelfand. Donkin has a proof that I really like, and some ideas from that I've sort of adapted into later things here. But sort of taking the BGG perspective, what emerged was the idea that, okay, even though the Weyl characters are finite dimensional, they're characters of finite dimensional modules, there are modules out there whose characters are in some sense easier. Now, they're infinite dimensional modules, and these are the Verma modules. But writing down weight multiplicities in a Verma module generated by a highest weight vector with is in a sense easier. And so we can view the Weyl character as a alternating sum of Verma module characters. And so this perspective then kind of propagated its way through various Lie theoretic settings. So there's various other algebras whose representation theory has the same weight combinatorics. And this idea was adapted. And so in particular, it was adapted in the setting we're interested in here today, the modular representations of reductive groups. So when you go to characteristic P, the standard modules you want to work with are not the Verma modules, but they're going to be these so-called Weyl modules. And Weyl modules are finite dimensional modules for G that are indecomposable. They're generated by a highest weight vector. They have a simple head, a unique simple head. So they're very much like finite dimensional versions of Verma modules. And their characters are given by the Weyl character formula. So when you're grasping at straws trying to find characters of your simple modules, and you have modules whose characters are given by Weyl's formula, these would be comparatively the easy ones, the ones whose characters are known. So the goal then is I take a simple module of highest weight lambda, and I want to try to express its character as a linear combination of these Weyl characters. And there are a few reductions that are well known if you work in characteristic P, or like anything in math, it's well known if it's known to you, and otherwise it's not. So one of them is Steinberg's theorem. This one says that if I have a dominant weight of the form, something that's P restricted, so I glossed over that slide, but so in theory, your eyeball saw X sub 1, but I didn't highlight it. It's a subset of the dominant weights whose coefficients are strictly less than P. So if I take a P restricted weight and I add to it P times any dominant weight, and I take the simple module of that highest weight, that's isomorphic to this twisted tensor product here. And so you can reduce the problem of finding characters for all simple G modules just to finding the ones whose highest weight is P restricted, and that's a finite set. We also know that the composition factors of these Weyl modules have a very strong condition, this linkage condition proved, Anderson proved the full strong linkage principle, but if L mu is a composition factor of delta lambda, then mu is related to lambda with this affine reflection relation. So if you're looking at SL3, and I was practicing this talk this morning in the hotel, and I realized that the wallpaper was completely tessellated by SL3 alcove. So I thought that was probably a good sign of something. I don't know what. I didn't go beautiful mind and start computing things on the wall, but I was tempted. So if you're looking at SL3, just to give an example of what's going on here, so there's sort of two sets of lines. These blue ones are the row shifted hyperplanes. The black ones are the original hyperplanes that the Weyl group's reflecting around. The green is the set of P restricted weights, so they're in that little region there. And then these larger triangles, these are what you get when you take these P translated reflecting hyperplanes. And so this up relation just says I have to, like, weights are related under this partial order if you can flip around these hyperplanes to get from one weight to the next, but the flips have to be a sequence of flips that sort of move upwards. So they go from the downside to the upside of a hyperplane. And so you see within the restricted region, there's not a whole lot that can go on with this up relation, right? The reflecting hyperplane line is right here. And so, you know, at best, you got two composition factors in your Weyl module. So these reductions enabled a very nice conjecture about Lusztig. And I want to say I'm trying to get better about math history. I feel like Verma should really be highlighted because from what I can see, Verma really saw early on some of these independence of P features that were crystallized in Lusztig's conjecture. But the conjecture was, and this was the big conjecture when I was in grad school learning this area, is that there are some coefficients for the decomposition or expressing the simple module in terms of the Weyl characters. And those coefficients, at least if your weight is P regular, so it's inside one of those alcoves, would be given by evaluating Kazan-Lusztig polynomials for the affine Weyl group of G. Okay, so this was the famous conjecture, and probably if you're, well, I mean, I think maybe Pramod said exactly this yesterday, I don't remember, but the big shock in the area was counterexamples that Riche Williamson found in this conjecture. So initially, the proof was the conjecture holds for a large bound of P, initially not produced, Phi big later produced actual bounds, but Anderson, Janssen, Zorgel using, I mean, there's many other names that should be going here, but they made the final link. Lusztig's conjecture is correct for all but finitely many primes for any group. This should say depending on, yeah, sorry, it's the Coxeter number. But what Jordy Williamson found in 2013, he found it appeared and published several years later, was lots of counterexamples that sort of showed that there will be no reasonable bound on P for which these coefficients are given by these evaluations of Combinatorics polynomials. Okay, so what next? So sort of shortly after that, Jordy, along with Simone Riche, found a different or conjectured a different formula, character formula. It was for different modules, and it's the modules that appeared in the title of this talk. So for every dominant weight, there is an indecomposable G module T lambda, which is the tilting module of highest weight lambda. These were introduced by Donkin in the early 90s, owing to a result by Ringel also. But the defining characteristic of these modules is the tilting module and its dual both have filtrations by Weyl modules. So that means if you want to study the character of a tilting module, since it's filtered by Weyl modules, you can express it as a linear combination of Weyl characters, but there's no longer going to need to be any sign changing. These are going to be non-negative coefficients. Question is, what are those coefficients? And so I think patterned after a formula that Zergel had for quantum tilting modules, Riche and Williamson conjecture that these coefficients would be given by something called P-Kazan-Lusztig polynomials. So they're like Kazan-Lusztig polynomials in a sense that they involve a change of basis. But the P-canonical basis, I was talking with Arun about this earlier, is, from what we can see, much harder to describe or characterize, at least as of right now. But of course, that may change. And this conjecture, they proved it in type A for P bigger than the Coxeter number. And then shortly after that, it was proved in all characteristics for P bigger than H by Achar, Makisumi, Riche, Williamson. And then a few years later, Riche and Williamson proved it for all P, which actually was better than their initial conjectured bound. They have a way to say what's happening in smaller prime. So, okay, so how did I get interested in this question? How does it connect to the things I was thinking about? Okay, get moving. So this was the link to me. So that was a formula for characters of tilting modules. And I started by saying that there was a long interest in characters of simple modules. So, okay, those are characters for different modules. How do we get back to the original problem? Well, it was pointed out in the first proof in 2019 that if the prime is bigger than or equal to 2h minus 2, and we can sharpen this bound now to 2h minus 4. Okay, so anyway, at the time this paper was written, this was the bound. Then you can get the simple characters for G from the tilting characters. And there were two different ways to do this, and credit is given to Anderson for this approach. So if I have a P-restricted weight, I don't want you to get lost in the highest weight here, but the idea is this. I take the simple module L lambda, and there's a tilting module with a certain highest weight. This precisely is the highest weight that's needed. And it is the projective cover of L lambda in a certain truncated subcategory of G modules. So these truncated subcategories, these would be examples of the things that Eric Friedlander was talking about, restricting these subcoalgebras. And then you can use some sort of a reciprocity there that says the Weyl multiplicities in the tilting module are equal to the composition, the number of times that L lambda appears as a composition factor in the Weyl module. So you can go from knowing the character of the tilting module to composition factors of the Weyl module, which you can then invert. The other method is very similar. It just involves restricting to a different place. And again, things that came up in Eric Friedlander's talk, this is restricting those finite group schemes, or in this case, we're going to take the first Frobenius kernel G1. Oh, by the way, being at the end of the week, I'm just freely using the fact that you've seen everything at some point this week. So G1 is the first Frobenius kernel. I take that and I slap a torus on it. And so what I can do is I can take that same tilting module, and when I restrict it to G1T, it's projective cover of L lambda, which is restricted as a simple module there. And then I use a different reciprocity. And here, this is a baby Verma module for G1T, and it really does, if you haven't seen these, it really does look like a baby Verma module, just cut off at some point. So those are two different approaches. And so because I had been thinking about these kinds of tilting modules a lot, what was kind of clear using a result by Partial and Scott was you could actually you could work this out for all P. So you could use the second approach, and even if you didn't know that that tilting module stayed indecomposable over G1T, there was a workaround using a higher weight tilting module. And just for full disclosure, there is another way you can go from tilting characters to simple characters using Ringel duality in types A through D. But in that situation, the group itself will change when you do your duality. All right. So, at the time that I had made that last little link, I thought, okay, this is, it's a very baby step to the bigger problem, but okay, is this mission accomplished? Did we do it? Did we get a character formula for the simple modules? And the answer is, well, in principle, but can you compute any of this stuff? So the first thing that's hard is the Peacock and Lusztig polynomials are difficult to compute. And I would reference a paper by Gibson, Jensen, and Williamson where they talk about this issue. And then this is becoming very indirect. You're getting these characters in this very indirect way. So, again, it makes me wonder in what sense is this a formula? So motivated by that, I started trying to think about, is there another way to get something that looks more like Weil's original formula? Now, when you're working with Dan, one of Dan's favorite expressions is, let's play fast and loose right now, which means let's just kind of generate some ideas. Let's not worry about what's 100% right. So I did something, I was kicking around something, I was like, what if you just stick some P's in Weil's formula? Would that give you, that is a formula. Does it say anything about anything you care about? And it would take probably most of you 2 seconds to figure out. It took me a little longer to figure out, which is like, no, you can, really what you're looking at is actually just the Weil character of the one weight over the Weil character of P minus 1 rho. And those don't divide unless lambdas in P times X plus. But then I thought, well, hold on, in characteristic 0, see these tilting modules which emerge in characteristic P, they do exist in characteristic 0. They're just the simple modules. There's only one kind of indecomposable module. This would be the quotient of 2 characters of simple modules in characteristic 0. But what if we switch that out for tilting modules? And that bottom character, that's the character of the Steinberg module. It's somehow the most interesting module in the world. I don't know, but it holds all of the secrets in characteristic P, and we understand some of them. It's every kind of interesting module you can have in this category. It's one of those. And so the question was, well, what if we just take the character of the tilting module of height by P minus 1 lambda, and we divide by this Weil character? I don't have to speed up here. The point is that it does perfectly divide the character of such a tilting module, because of the reason that's above, but I'm not going to worry about that. So we have this thing that's called the Steinberg quotient. This is T lambda. And so T lambda is an element in the W invariance of ZX. That means it has coefficients. You can express it as orbit sums of weights. And so the question is that what are these coefficients? Now, all this is doing is repackaging the problem of finding baby Verma multiplicities for these tilting modules. But it's just a different way to look at it. And maybe combinatorially, that's what we need to do. So there's some immediate facts you can find. The first thing is that the orbit of S lambda, that's the largest orbit, it appears once. And then all the other orbits that could appear in there, therefore weights mu, where mu minus rho is linked to lambda minus rho. So the kind of first result in this direction was that, in fact, every weight that can appear does appear in this character. And in fact, it appears in this monotonic way, just like those Weil characters. As you move in from the outer orbits in, the weight multiplicities can only go up. And the proof of this used ideas from a paper by Ye and Dodie Sullivan, and it was, I credit Steve Donkin for pointing out that this would be the right way to look at it. Okay, I am going to be out of time in a minute. So what I want to say is these characters come from a single representation theoretic property of tilting modules. If you take the tilting module whose highest weight is given by this, and you tensor it by a twist of the Weil module, it has a Weil filtration. And you can use a couple things about characters. And the idea is that what you're going to do is you're going to show that this, I'll just cut to the chase here. You basically show that this Steinberg quotient, when I multiply it by any character of the form P minus 1 rho plus P gamma, and I use 2 identities. I use Brouwer's formula to tell me how an orbit sum hitting a Weil character, what that looks like. When you do that, it looks like a bunch of Weil characters, but these weights are no longer necessarily dominant. And so you can straighten them. Oh, sorry, go ahead. Oh, S mu is the orbit sum of mu. So it's mu, yeah, in the, yeah. Yeah, sorry, I'm going too fast
You
for.
take into account the isotropy, or you just take some W mu?
Just sum over all the weights in the orbit, yeah.
I see.
And then some of those weights will no longer be dominant, and so you straighten them using this straightening rule on these characters. And when you straighten them, you may pick up a negative coefficient. But the whole thing, when you multiply T lambda by this weight, it has to be given as a non-negative sum of Weyl characters. So if you picked up a negative coefficient when you were doing S lambda and you straightened it, you need to add an orbit inside that's going to offset that negative. And you keep building your way in. All right, now I'm going to have to really jump to the end here. And so the other thing that I was shocked to find as I did this is I found that the coefficients here, you can do this for quantum tilting modules also, and the coefficients of the Steinberg quotients for the quantum tilting modules will be given by evaluating Kazan-Lusztig polynomials. So I was like, oh, great, I just got back to the original problem. But we're looking at it from a totally different perspective. And so what I did is I said, okay, let's take that straightening rule I just said a second ago, and let's find the smallest character that obeys the straightening rule. And let's see, I just had a computer program run it, what would be the weight multiplicities of such a character? And when I ran the program, I found that the weight multiplicities were almost exactly what was predicted by Kazan-Lusztig polynomials for very non-trivial examples, but you're doing it from a completely different perspective. You're not using any of the high-powered results that tell you that link Kazan-Lusztig polynomials to these representations. So these characters are somehow very interesting. They're very close to things that would be given by Kazan-Lusztig polynomials. And so now the question is, what are these counting? And I'm hoping to eventually, yeah, I better stop here for now. I'll take questions and then if there's something. All right, thank you.
Let's go. Any questions?
So Kazan-Lusztig polynomial for the affine Y group or the finite Y?
The Kazan-Lusztig polynomials?
Yeah.
For the affine boundary.
Yeah.
Yes, absolutely. Yeah. Yeah, so it's really the same, you're getting the same coefficients that Lusztig would say for that, but now it's just they're all positive, you're not having, yeah.
Yeah, okay, thank you.
Yeah.
Well, you asked your first question already yourself. What are these counting?
So, yeah, I was talking to Arun. I want to go back to a paper that I have with Arun, and I'm trying to figure out why are these almost giving you what a Kazan-Lusztig polynomial would give you. It's way too close to be arbitrary. So I'm trying to understand what are the straightening rules when you're computing Kazan-Lusztig polynomials, and what are the straightening rules when you're dealing with these weights, and what's this missing that the other one's counting that's somehow giving you a little bit more sometimes. But yeah, I would have loved to have gotten that figured out by now, but I'm taking collaborators if you're interested in applying.
I'm sorry, I've never worked in stuff before, so this might be a really stupid question. Either these Weyl models or maybe the Steinberg quotients, is there a way to write these as some type of a J lower street functor applied to something? Like in the sense of like my partial stop maybe?
That's a good question. I don't know. I'm looking at the person sitting right behind you as maybe somebody I'd want to talk to. That's not a dumb question. I'll start with that. But yeah, I don't have a great answer to that. That's a good question.
I see.
Oh, I'm sorry. You're talking about the Weyl modules themselves. Oh yeah, I'm sorry. I misunderstood the question. Thank you.
So.
Okay, I'll probably wish you a sum of that's the slides. So let's move the schedule and we'll get ready for the next talk.